Good evening. Welcome to Community and Technology, where we connect the global community with news, information, and resources that we hope will help improve your life. I'm Stu Reid, here with my co-host, Dave Burstein. Hey, Dave. And we have a very special guest today that I'm going to let Dave introduce. Dave, please introduce our esteemed guest.
Well, one of the most interesting things happening in the world of hardware, not software, is how suddenly some key pieces are becoming open source and available to everybody. And we've got somebody who's in the middle of it. RISC-V is an attempt to, not an attempt because it's actually doing it, and we're starting to see product, to give people an alternative to the Intel or ARM processors in our computers and phones. So why don't I ask our guest to introduce herself and what she's working on that you want to know about. Take it away.
Well, thank you, Dave and Stu. It's a pleasure to be here. This is Calista Redmond. I'm the CEO of RISC-V International. And I've got a long history in hardware, and especially around bringing open source, something that we've known for at least a couple of decades now. And thanks to Linux in the software world, we're bringing a lot of that ways of working, ways of collaborating in the open with transparency over to the hardware side of the house. And so that's an exciting area that we'll dive into as we talk more about RISC-V.
Give me some particulars. First of all, what's happening? Are there actually chips happening? Who's making them? What's going on out there in the real world that is probably a dream you had 5 years ago?
You know, let's go back further than 5 years. Just a quick breeze through history. So back in the 80s, there were the first set of processor wars. You know, computers were starting to come out. They were really big computers, whether it was a desktop with that looked more like a suitcase that they called portable, or a mainframe, or servers and things that went in the data center. Those processor wars of the 80s really kind of landed on a common variable called power. They had a constant supply of power. They were always plugged into the wall. You could make them as big and as powerful as you wanted to. And at the end of the day, Intel really won. They owned the entire design to production capability in those microprocessors. Then about 20 years later, see, I told you I'm going to fast forward a little bit here. We started to unplug. We started to get mobile. We started to have laptops that relied on battery power, and you no longer had that energy supply. And ARM really came in and started to take what has been sort of referred to as the low end. But, for me, my phone is pretty essential in my life, probably yours too. But ARM really started to steal the day then. So if you look across time, there have been about 50 different microarchitecture ISAs, instruction set architectures. It's kind of the base blueprint of what all microprocessors are designed on. There have been about 50 of those. And until about 2020, 99-point-something% of the industry ran on two microarchitectures, Intel or ARM. Well, RISC was a processor design developed in the 80s that our friends over at Berkeley dusted off about 11 years ago and said, well, you know what, this would be great to learn on. Our students could take this from idea to tape out and really, kind of learn from that experience and be, much more productive once they hit industry. Well, a lot of universities really love that. And some industry started to love that too. And they said, you know what, let's take this open source. Let's open source a microprocessor, which had been done a handful of times before, but this time it's really taken off. So to answer your question, you can find RISC-V now from embedded to enterprise, in cars, in high performance computing, in earbuds, in many other pockets and corners that is really starting to take off and becoming a formidable third architecture, if you will, in the overall scheme of things.
Let's talk about 2 or 3 of those places. What's happening in cars? What's happening in earbuds? Who are the people or the companies actually doing this? Give us some particulars.
There are more design houses on RISC-V now than any other architecture in history. This has become the place where you can be an entrepreneur and go after these new corners and new pockets of opportunity, like earbuds. We didn't have earbuds 20 years ago. We had things that had a cord attached to maybe even a Walkman, right? And so, you've got about 2 million cores going out every month from earbud type manufacturers. Cars. So cars have things that mechanically operate a car versus things that are there for infotainment. Both are huge selling features of a car, whether it's safety and security or other aspects. These are all extremely important in the automotive industry and very competitive and kind of mission critical, right? There are a lot of ISO safety and security standards that need to be adhered to, especially enter in new types of driving like autonomous vehicles or assisted driving, where things are even more mission critical because you don't really want to drive over the cat or the squirrel or some kid's ball that rolls into the street. So all of these things are very important and kind of brings out the nuance of new capabilities, new opportunities, and that's where you start to see RISC-V the most. If you've already sunk millions of dollars, hundreds of engineers into an existing architecture, saying, hey boss, I want to swap that out for something new, that's a big bet to place. If you're saying, let me use something that's free and open and has no design constraints to go after this greenfield opportunity, that makes business sense. And it also, by the way, makes technical sense. You look at those proprietary architectures, as we get into the technical weeds here, they have like 1,500 instructions in the base model. Think of it as you get the whole burrito. RISC-V has 47. Do you want to deal with 47 or 1,500 to just start, to just begin to design whatever it is that you're imagining you want to add on to your existing investment for that competitive feature? So we've made things more modular. You don't need the whole burrito. Here, how about just the rice, and you can add whatever you want to on top of it around that. So
now we're going to come back to that, which is what is RISC, what is CISC, and so on. And I'll probably just explain it a little bit. But our guest just got up for some reason. She'll be back. Yeah.
No, I'm here.
She is.
There was some extra noise outside the door, so I closed the door.
Yeah. The stuff that's interesting to people who aren't into micro instruction sets is how the heck does something like this happen and how can it compete with the 2 or 10,000 engineers that Intel has designing this kind of stuff? Where does it come from? Who's writing it? Why are they doing this when they're not getting paid? Tell us a little bit about the process of developing this.
So everyone wants to be wildly successful in whatever their commercial endeavor is, right? It's an entrepreneur's dream, a venture capitalist dream, a multinational's dream. Everyone wants to go to market and be wildly successful with whatever that vision is. You also want to take as little risk as possible in developing and cultivating that solution. And by the way, if you can get to market better, cheaper, faster, that would be great too. RISC-V is sort of the model that helps achieve a lot of those things. So there's no licensing fee. So there's no royalty that you pay back to one of those proprietary solutions every time that you send out your earbuds or every time your processors go into another phone or into a data center, through a server. You don't pay those royalty fees on RISC-V because it's open, it's free, anybody can use it. rather than spend 2 to 3 years negotiating an architecture license to be constrained through a future royalty model that's ascribed to that agreement. You don't have to sign that. You don't have to pay those royalty agreements. You don't have to spend those 2 to 3 years negotiating. And you don't have to have 200 to 300 of your own engineers designing that solution, because you can pick pieces, building blocks from the open community to get a running start, and then just simply add your differentiation, your secret sauce on top of and around that, and then bundle that thing up, go to market, and be wildly successful. And the more successful individual companies are in our community, the more they invest, the more we build a set of shared-based building blocks that everyone can use, the more adoption happens that then in turn drives demand. So it's a cyclical part of business that continues to kind of self-fulfill as companies, organizations, universities, research organizations, governments even continue to invest back into the base. You know, on the government side, you know, everyone wants to have a great digital technical economy. You see it in Europe with the EPI initiative as an example. You see it you know, throughout the world, in the US even. DARPA puts a tremendous amount of funding into universities to cultivate these shared-based building blocks. So that's something that's been going on for decades. And we're continuing to see that, to permeate that into the hardware space as well. So this business model becomes that competitive advantage in addition to the ease of design by having a more compact set of base building blocks.
Now, let's take that to the extreme. We happen to be based out of City College here in New York, which has a superb engineering department. If one of the listeners here happened to be a student in the engineering department who could do some chip design, how could that individual, just for the heck of it, get involved with your organization? How open is it really to new people?
Yeah, there are zero barriers, really. I mean, an individual student can become a member, a university can become a member. Those are all free. And by the way, there are hundreds of universities that are flipping their engineering curriculum from other architectures onto RISC-V because they also see the full transparency of this open model as being able to teach the underlying RISC architecture, which is, you know, been fundamental since the 80s, and to enable their students to become, you know, to hit the ground running immediately after they graduate. So students are designing already on RISC-V. There are, you know, HPC cluster competitions that are being, you know, cultivated with RISC-V. There are always a couple hundred at least positions open on RISC-V. Every time I, you know, kind of do that little keyword search in LinkedIn, and that's just in the US, but it's happening globally.
Tell us more about the global, because that turns out to be one of the most important things. How much of this is being done in the US? How much of it's being done in Europe? How much of it's being done in Asia?
That's like a perfect way to phrase that question, because it's 1/3, 1/3, and 1/3. So we really are very diverse that way. And, you know, and there's some, kind of fluctuations in countries, but it's basically a third, a third, and a third. We have grown tremendously. We have actually seen our membership over the past few years growing around 130 to 133% per year. Like a lot of companies in that, they like to see, you know, 3 to 5% growth. Double digits would be great, but triple digits, yeah, we're multiplying every year. That's how rapidly adoption is happening in RISC-V, investments happening in RISC-V. Remember when I talked about that companies like to lower their risk of investment? If everyone is investing in RISC-V, then it becomes a stronger bet to place, right? If all of your technical dependencies are on one company that controls that architecture, that's a higher risk scenario. Because, you know, as we've seen across time, architectures go away, architectures morph and change hands. There's acquisitions and divestitures and other types of activity that go on in the hardware side of the business, in any business, right? You never want to have all those, eggs in one basket, if you want to go back to those analogies, right? So by everyone investing in it, we all have a shared sense of responsibility and investment to the success and the long-term durability of that solution. And by keeping it open and completely transparent to both the members and non-members, we can continuously improve and update and upgrade the pieces that are possible to do that. And we invite broader perspectives as we solidify and freeze those elements that then become global standards.
Lisa, you talk about members. What does membership entail, and what is the significance of that?
So it's very much like any open source software organization where you have tiers of membership, and we have free membership for individuals, universities, nonprofits to engage, because we feel like they're helping seed the industry with talent, and that's really important. We want to help support that. Then we need to support how we maintain and progress the technical state of the art. So we need some fees to help do that. So there's a base level of membership called strategic, and you pay based on how big of a company you are. We even have a startup tier. And then there are folks who really want to strategically support RISC-V for the duration of time. And that's called our premier membership tier. And they get a seat on the board that makes a lot of business decisions, as well as on the technical steering committee. Now, everyone can earn a seat. You can always earn a seat through leading committees, leading work groups, and then therefore, or being elected to different roles of governance. So that shared governance and that shared decision-making helps to ensure that when we freeze a spec, that we make a global standard, that it will stand the test of time. It is not solely reliant on a single company's technical agenda. It is the shared collective that is putting these things forward. And that's why membership is, number one, important, but number two, it's important that you have strong governance in RISC-V or in any other type of open source endeavor.
We're going to take a break in a few minutes. I want to spend the few minutes after the break. One of us is going to try to explain CISC versus RISC and why this is called RISC and things like that, and start looking at the international implications, because China and the US are in a Cold War in technology right now, and all those are interesting. But let's talk a little bit about, it's not interesting, the politics? Well, you'll tell me why it's not interesting, and we'll have that out later. But let's get people some perspective first. Is this possible for something crazy like this, chaotic like this, to actually work? Did it work for Linux? And why? And is that a model we can expect here in hardware?
Yes, we can. So if you look back to 2001, about that time, Linux was sort of viewed as, an experiment, right? It's something that people do in their free time. It's an interesting alternative to a Windows or a Microsoft type software that is basically going with every system that comes out. And they said, well, maybe there's an alternative. In 2001, IBM said, well, I'm going to put $1 billion on Linux. And that was a turning point in history, right? Because IBM has their own software business, but yet they said, you know what? If we invest in this open model, that will kind of open opportunity and remove barriers for the entire ecosystem, right? So this past February, we had our Linux moment. Intel, who also has their own architecture, said, I'm going to put $1 billion on RISC-V because they want to see it succeed in addition to their own architecture. There is room in the industry for multiple architectures. And they said, you know, we're putting $1 billion in on this. We are continuing to see the acceleration of RISC-V across the industry. So my answer is yes. We've had our Linux moment. We are progressing down that same path where, today Linux underpins most of the major software in the world. Banking systems, airlines, everything would come down if it wasn't for Linux. It rides on everything. The same thing is possible in the end-to-end compute spectrum that you could one day find RISC-V and everything as a microcontroller, as a primary processor, helping with storage, helping with IoT, helping as an accelerator. There are many parts of this equation that are ripe for RISC-V, and we have indeed had that moment.
And we'll hear more about the practical end of this. And maybe we'll explain some of these technical terms that have run by, because some of this stuff is really interesting. I mean, what's a reduced instruction set and why do we care? After we take a break. Stu, can you bring on the music?
Sure. Thank you, Dave. This is WHCR 90.3, the voice of Harlem. You're listening to Community and Technology, Stu Reid and Dave Burstein, and special guest Calista Redmond, CEO of RISC-V International. Be right back after this brief break. Stay tuned. Okay, we're back. We're back with Community and Technology on WHCR 90.3 FM. Stu Reid, Dave Burstein, with special guest Calista Redmond, CEO of RISC-V. Before the break, Dave, we were talking about kind of breaking down what is RISC and why do we even care?
I think I'm going to take it because if we let Calista explain it, we'll be listening for 20 minutes to some of the bits. RISC happened, I'm looking it up, MIPS, Sparks, etc. In the 1970s.
They were all birthed in the 80s.
Okay. Wikipedia says it began with the IBM 801 in the late 70s, then went to Stanford MIPS and Berkeley RISC and so on. What this was all about is that the computers inside our PCs back then, and all of the computers had been adding power and processes and different things they can do, instructions that the computer could run, to the point where it got awfully complicated. And a few folks, I knew it was Stanford and Berkeley folks doing it. I didn't realize IBM was there before until I looked it up here in Wikipedia. Decided, heck, if we get rid of a lot of this stuff, we can make something that's real simple and we can let it run really fast. And then we can do some of these things in software instead of hardware. And that was a revolution in computers back in its day. And we wound up with Sun Microsystems and everybody else with the fastest workstations out there at a fraction of the price of, say, IBM mainframes and DEC mini computers that did the same thing, because the simplification was good. So that was what RISC was. It had a much simpler design, moved some things out of hardware into software, and suddenly ran much faster and was simpler to produce. Now, that kind of design comes from a company called Advanced RISC Machines, ARM, whose design and software, or the design modeling, is the software that builds the hardware that's in the chip in essentially every single cell phone in the world. 1.4 billion cell phones were produced last year, and I bet at least 1.3 billion of them had this reduced instruction set inside it. On the other hand, my PC has a complex instruction set, Intel architecture, and it's been going back and forth since the 1980s, which is better. Each side has been adding some of the features of the other side and so on. But what you have there in general is a simplified design of the hardware so that it's only 100 million transistors instead of 15 billion. Although actually the 15 billion number is what's going into the processors being used in, say, the latest Apple cell phone, because they add and add and add. So you've got this simple core that does the basic computing, and you can add to it. How much of that core does RISC-V introduce, Calista?
So, like the examples you gave, RISC-V is a standalone architecture. You start with a RISC-V base set of instructions, 47 instructions. And, by comparison, some other popular architectures ask you to start with about 1,500 base instructions. So it is a lot simpler to start with, but it's modular by design. Most of those other architectures have incrementally added on to their base over time as they've come out with additional capabilities. So we've actually taken a simpler approach, a more modular approach rather than incremental. And that's where you have some of that design flexibility that really allows you maximum design freedom. You don't automatically have the burden of instructions that are not useful to the design that you're trying to implement.
And so if you want to make something that has to be really small because it fits in your earbud, how does your software relate to that, and what do people have to do to use it?
So folks have found, you can design with any RISC architecture, or, you can gain a license from or permission from Intel and AMD to kind of go into a CISC approach, and ARM as well, right? The essential elements here are that having design flexibility helps you to dial in for the performance, the power, and the capability that you're specifically looking for without that additional code complexity, as you've pointed out. So, if Moore's law, once upon a time, the race for semiconductors was all about price and performance. And now that design flexibility is really becoming a key variable in figuring out what approach to take for the workload challenge you're trying to solve.
And could you use it if you were Elon Musk making an automobile? Where would it fit there?
You absolutely could, and I would think that in automotive, you continue to use it for some of those safety critical features. You could use it in infotainment. You could use it anywhere you like. The number of processors continues to increase in automotive, just as it does in your cell phone. There could be a dozen processors in your cell phone right now. In every instance, there is an opportunity to design compute using an instruction set architecture. Picking which one you're using doesn't determine a limited set of use cases where you can use it.
Now, if you say that in the car that Elon Musk is building, there are going to be 25 processors, which is actually probably a low number for how complicated cars are these days. A little low, whichever. Do they all look the same? Or what's the differences between them?
Well, there will be some that are designed for higher power consumption and extreme performance, and perhaps some parallel processing. And then there will be some that are very lightweight. They're trying to take a little bit of data, do some quick processing, and not have to burden some storage or cloud facility in using that. I am not an engineer, so explaining further than that on the nuances of various chips used in a car, may be best left to some experts in those fields.
But the sense is that you can take this processor, if it's RISC-V or ARM or whatever else it may be, and you can add to it the designs you need to, for example, take the LiDAR and radar and visual information coming into the car at billions of observations a second, literally, in order to do an autonomous car, and add some chips that can do that really fast and incorporate it all around the processor, so you don't have to design the processor. But you can also have it there running the radio in the car, virtually off the shelf, to which you add power amplifiers and anything else you need for the radio. And it could be sitting there in a very simple form as a sensor noticing the tire pressure and recognizing when you have a problem with the tire, and that can be designed to be very simple, very small, very cheap, all working off the same core, which is RISC.
I thought you were going to take that in a slightly different direction, and that, when you have your radio, your stereo system connected to your tire pressure, that it would know that when I'm driving really fast on the highway, I need that music turned up. And if I'm slow and in rush hour traffic, maybe switching to something a little calmer would be better. But, you could also understand whether or not you've got a low tire. I understand. And I agree.
And that's the kind of imagination, I never would have thought of that, but she did, that is possible now when you have a flexible architecture that's available that can use any way you darn please. And in fact, take it, Calista.
And you may want to use that tire pressure module that you developed for an automobile and use it in a bus, use it in an airplane, use it anywhere else there might be a air pressure situation that you want to measure. By adopting an open approach with design and license flexibility like this, you can go off and move into those adjacent markets with not only the technical flexibility, but also the business opportunity.
What's some of the most surprising applications you've seen out there?
I've seen a welding pen. I thought that was pretty good. We see lots of experiments. We see lots of ideas coming up. I think that, as we continue to put microprocessors in everything from, toothbrushes to refrigerators to high performance scale out computing to cloud computing to automotive, any corner you can put a processor seems to be getting one and has opportunity for RISC-V.
Now, any corner, any location, how about any part of the world? Are we seeing any of this being used, say, in Kenya or South Africa?
We don't have a huge membership coming in from Africa or South Africa just yet. I do need to remind you, though, that anyone, anywhere, member or not, can download and use RISC-V. Once you contribute something, you go onto GitHub and you can just download. Here's the instructions. It's a set of text. It's not difficult to attain. But what is true about open source is once you contribute under an open source license, anyone anywhere may download and freely use that. It is collaboratively and collectively produced, and so therefore it is not controlled or owned by any one company or entity of some kind, right? So once it's contributed, it's globally free and available to use. So you go to Creative Commons, right? And you can download any piece of art that you like or any piece of text. In fact, our base instruction set architecture is under a Creative Commons license that anyone may freely have access to that.
Let me make that concrete. Would I now in my computer, I'm using my phone for this video, take my computer, go to the user repository called GitHub and get the software or the design of the hardware in 5 minutes or 5 hours? I don't know how big it is and how fast my connection has to be.
You could download that pretty instantaneously.
And you could have that before the show is ended if you've got a fast connection. Reality.
You certainly could. Now, and I want to just highlight for you a couple of notes that I think are important for your listeners. No single company or country would ever wish to invest deeply in a technology that furthers, society, furthers the technical progress that could then in the future be blocked. And that's something that is a concern, whether that architecture is being bought and sold through acquisitions or divestitures, or because of the sunset of that particular technology. Most technologies have somewhat of a life cycle. And no one would ever want to have, concerns about their supply chain or concerns about their development partners or be blocked in market opportunities. So companies have elected to take an open approach to most things, right? I mean, hallucinate for a minute that you decided to get into the electrical plug business and said, you know what, I'm going to make a new electrical plug. That's probably not a wise investment. But if you make an investment that says, I want to be able to plug into what has become a global standard, that makes a lot more sense. And that's where RISC-V is not construed as a technical asset of any one country or company, but is thought of more as a global standard. That whether you're a U.S. company or a startup in India or a multinational automotive in Japan, you think about, how do I interoperate in the world? What is my global opportunity for partnerships, for development partners, for supply chain, for market opportunity, things like that? And you make those investment decisions.
Stu's going to cut us off in a minute or two. Let me just make this concrete. The alternative to RISC-V is the ARM architecture, coming from the Acorn RISC machine was originally what ARM stand for, because the Acorn made the BBC Micro and developed all that stuff. BBC Micro is long gone, but the architecture lives on. Japanese company SoftBank was going to buy ARM, and suddenly the British decided not to let that happen because the British didn't want to lose control of ARM. And what you're just hearing from Calista is something that's this open source, is available to anyone, anywhere. And that's a big advantage. Stu, why don't you take the last question and then give Calista a moment for final thoughts.
Well, my question is, and I think it's really laudable what RISC-V is doing. And you talked about, a global membership, and I see that you are a global nonprofit association. How are you able to maintain it? Is membership fees, is that what keeps you guys going? How are you able to sustain your organization and the advocacy for RISC-V? How does that happen?
I would say and give most credit to the members themselves. If there isn't market demand, if there isn't technical collaboration going on in the community, if there isn't commercialization of RISC-V solutions, then there's really no purpose in us as a central organization. We just become like another fun run or bake sale, right? Like you don't do RISC-V just because you need a new hobby. You do it because you want to build and grow commercial success or talent and growth. And, there are many stakeholders here in the technical sphere. And that's what makes our role very important. Our role as an organization is really to help guide and organize the various technical efforts of the community. We have about 60 different technical work groups that are continuing to build, some of those open-based building blocks that anyone can use. And so that helps countries and companies around the world, continue to invest and see promise in RISC-V.
Okay, well, we're just about out of time. Calista, is there anything that you might want to say about RISC-V that we haven't touched on before we close?
Well, I appreciate the time to join with you in conversation. It's been a wonderful opportunity to share with your listeners what we're doing at RISC-V. If you want to learn more, please find us online, RISC-V.org, and also, contact or reach out to us on social media. We'll be happy to connect with you.
And let's add to that, if you go to the site, what's the site, Calista?
RISC-V.org.
You'll also find that the week after next, they're going to have a conference, much of which is online. How much does it cost for somebody to attend?
Well, next week we have one in Paris, and the week after that, I'll be speaking at one in Tel Aviv. And like last night at around midnight, I was speaking at an event in India. So we have a lot of events, and there are many to pick from, and we have many of them promoted on our website.
And Paris,
with the current scenario, there are many opportunities to join us virtually at any of those forums. on deep dive technical topics or to learn about some of the business opportunities.
And how much does it cost if somebody wanted to attend online the Paris conference next week, which has a really
That's a
strong
pop
program?
quiz that I would have to look up myself.
I suspect
I
it
will,
may
I will
even
be there
free.
in person.
Yeah.
Wow.
This is something happening that I bet not many of the listeners here have heard of. I wanted to bring it because it was something interesting and different. Thank you, Calista.
Okay,
welcome.
you can find the details of that spring 2022 RISC-V week in Paris on their website, RISC-V.org. I want to thank Calista Redmond, CEO of RISC-V International, for joining us today. Thank you, Calista.
My pleasure. Thank you.
Okay, and thanks, Dave. You've been listening to WHCR 90.3 FM, the voice of Harlem, community and technology. Stay tuned next week, every Wednesday, 5 to 6 p.m. Thanks for tuning in. Good night.